zeta potential, and colloidal stability. The zeta potential is a physical property exhibited by any charged particle or macromolecule in suspension. It can be used as a parameter to optimize the formulation of suspensions, emulsions, and protein solutions, predict interactions with surfaces, and optimize the formation of films and coatings. The zeta potential is defined as the electrical potential at the slipping plane. The zeta potential provides information on the expected colloidal stability from electrostatic repulsion between particles. However, it does not give information about stabilization by steric effects. If all particles have a positive or negative zeta potential, they will repel each other. If otherwise particles have low zeta potential, they will tend to aggregate. Interparticle interactions are the sum of attractive and repulsive forces. Colloidal stability requires repulsive forces, either electrostatic or steric, to be dominant. Particles can aggregate irreversibly like in coagulation or reversibly like in flocculation. Laser Doppler electrophoresis is one of the methods to estimate the zeta potential. This method measures how fast a particle moves in a liquid when an electrical field is applied. During the experiment, the sample is placed in a cell and an electric field is applied. Charged particles are attracted to the oppositely charged electrode. A laser beam is passed through the sample undergoing electrophoresis, and the scattered light from the moving particles is frequency shifted. The frequency shift is directly proportional to the electrophoretic mobility of the particles and hence to the zeta potential. The zeta potential is related to the electrophoretic mobility by the Henry equation. In polar media with moderate electrolyte concentration, the Smoluchowski approximation can be applied, whereas in nonpolar media, the Hawk approximation is used. Physicochemical parameters such as pH and ionic strength have an influence on zeta potential. The isoelectric point is the value of pH at which the net charge is zero, and therefore the colloidal stability is minimal. The isoelectric point is determined by estimating zeta potential as a function of pH. Particles with zeta potentials more positive than 30 mV or more negative than -30 mV are expected to have good colloidal stability. The thickness of the double layer, defined as the Debye length, depends on the concentration of ions in solution. The higher the ionic strength, the thinner the double layer. For more information, visit us at iqac.csic.es/qci/.